OK, so the plan for this talk is to discuss graph algorithms, but kind of more from the perspective of combinatorial data structures and combinatorial algorithms. Well, the motivation of this talk is still very similar to all the talks we saw before, is that we have some very large graphs and networks. So they come in the form of the standard ones are from scientific computing, so that you get basically meshes, you're trying to do physical simulations, and they can be thought of as very large sparse graphs. More recently, we've been doing this to images. So your standard image, your ocean surveillance satellite, that's about 10 to like 16,000 by 16,000 pixels. And your standard medical image, you're looking at about 1,024 cubed or even more. So we're looking at about easily between 1 billion vertices to 1 trillion vertices now. And then we had this wonderful thing called social networks, where any person can create several accounts, and then they can start friending each other. And once again, we're looking at graphs in the size of billions. So to deal with all these large graphs, there has been a lot of work over the last 3 or 4 years building better graph processing systems. The problems being solved in these, they're still very much kind of the things we like to do in undergrad graph algorithms to graphs. So things like shortest path, things like max flow, min cut. Sometimes we also like to do things like PageRank or inference on graphs, so we start doing optimization on graphs. And the approach that has been, the prevailing approach that has been used for these problems is let's build better systems. Let's build better, more distributed, better hardware, more GPUs, just more powerful graph processing systems. And this has worked very well so far. On the other hand, you started seeing papers like this come out, which basically the title is Theoretically Efficient Parallel Graph Algorithms Can Be Fast and Scalable. And what they say is that this is a paper out of CMU at SPAA Symposium on Parallel Algorithms and Architectures last year. And what they say is that theoretically efficient parallel graph algorithms can scale to the largest publicly available graphs using a single machine with 1 terabyte of RAM and processing them in minutes. And if you're familiar with the graph system type of things, these numbers are at least competitive, if not significantly better, than what we have been able to do to, say, trillion-edge graphs. And this suggests that when we think about graph algorithms, we should at least think in terms of getting very good provable running time bounds. And in this talk, I will take this idea a little further, which is to say that if I want to design provably fast graph algorithms, what I really need are certain ideas and concepts from data structures. And I need those ideas to get really efficient graph algorithms. Plan for the talk is I want to talk about the underlying phenomenon that underlies all inefficiency and efficiency of graph algorithms, which is really, I like to think about this issue as dynamic pathfinding. Then I'll discuss 2 instances of this phenomenon, one of which is the max flow problem, and then the other is dynamic matchings. I'll now finish with some conclusions. So the problem that I will motivate with is this node classification problem. This is one of the most widely used benchmarks for measuring a graph embedding or a graph learning system these days, which is that I just have a graph. I have some edges between people. Some of the vertices are labeled plus, some of them are minus, and some are question marks. And I want to label the question marks as well as I could. Our current understanding of this problem compared to things, you can think of this problem as the analog of classification of digits, classification of images, except this is a graph problem. And compared to our understanding of what we can do to, say, images or voice or sound data, what we can do to graph theoretic data is actually quite terrible right now, in that the current best kind of classification accuracy we can get on standard benchmarks like the YouTube graph or the blog catalog graph is somewhere in the 40% range. So this is one of the kind of classification problems, if you ask me, which is the classification problem where our current best numbers can be significantly improved. This is one of the ones I would hazard to guess that you can do a lot better. But because I'm trying to stick to kind of more well-known graph algorithms, instead of describing the 40% algorithm, I'll describe the 25% algorithm, which is p-norm semi-supervised learning. This has the advantage that it's extremely simple to state. And what it does is that it takes all the unknown vertices, takes the value at the unknown vertices, treats them as just unknown variables. And all it does is it just minimizes over the unknowns. subject to the known variables of the difference of the labels of the vertice and its neighbor taken to some power p. This is known as p-norm semi-supervised learning. And it's directly related to spectral graph theory, the Laplacian operator, Markov random fields. It's related to a lot of things. And this will be our starting point. In fact, I will actually take an even simpler version, which is the p equal to 1 case with 2 terminals. The p equal to 1 case with 2 terminals, this is the max flow problem, or the min cut problem. I have one terminal that's labeled plus, one terminal that's labeled minus. And I want to just label everybody else either plus or minus to minimize the number of edges with different endpoint labels. It's a little bit non-trivial to show that the solution to this is still integers. This is actually a fractional problem. And if you take general p, you will get fractional solutions. But p equal to 1, because of this kind of connection to sparsity and so on, you are going to get a cut. And the solution can essentially be represented as this blob out of S. You're just finding a subset of vertices containing S that minimizes the total number of edges leaving. This problem got studied a lot in operations research. And it turns out that it also has a very nice dual, which is you're trying to route the maximum number of edge-destroying paths from the source to the sink. And this is basically the min-cut max flow or max flow min-cut theorem. There's a bit of a funny history to it in that this problem was initially studied on the Russian railroad network. And the cut they found was essentially, I mean, if you look at the map here, it says somewhere this is the Baltic Ocean, and here's the bottleneck. They literally realized that, hey, if I want to disrupt the network, it's roughly the same as trying to route the maximum amount of traffic through it. And the people that were also trying to route traffic through it said, hey, we're really just finding the min cut as well. So the way that this gets solved is you just solve it like a routing problem. You say, hey, while there exists a path from the source to the sink, route the path. Right? So if I can find a path, I route it. Except in this example, you can take a very bad path. You can take a path that blocks off both of these paths. So greedy is clearly suboptimal. And what do we do to make greedy work? We correct the greedy. And the way we correct the greedy is through this notion of a residual graph, which is the idea that once I found this bad path, I can find a good path that cancels out the edges I took in the wrong direction. So the idea is that you have this iterative procedure where you find a path. You reverse all the edges that you used on it to indicate that, hey, I can go undo them and go in the other direction. And I repeat. And this is kind of the simplest, I claim. I claim, one of the simplest iterative algorithms for converging towards the solution of an optimization problem. The idea is I find a path. I adjust my graph. I find another path, and I repeat. And in many ways, this captures the difficulty of designing efficient graph algorithms, which is that I could have a class of graphs where I need to find a lot of paths. Imagine I can have a graph where S and T are extremely well connected to each other. And as a result, I need to route a lot of paths. At the same time, I can also have a graph where the diameter is huge. And the huge diameter means that for every path I find, I need to touch a very big chunk of the graph. So I actually need to have very long path as well. And if you just take the product of these two numbers, you're getting n path times n edges, which on large sparse graphs with billions of edges, you're looking at somewhere between 10 to the 15 to 10 to the 18 clock cycles, which is hugely expensive. So we don't want to do this. And essentially, a lot of the the cleverness in designing better graph algorithms is how to get around this phenomenon of I want to find n paths, each of size n. And by the way, this also has analogs in numerical iterative schemes in that most of our favorite iterative methods, things like conjugate gradient, accelerated gradient descent, also runs into very similar bottlenecks. And in fact, for some of these problems, if you actually plot the solutions, you can actually see that solutions essentially look like the updates. You look at what the updates they're making, they essentially look like they find a path, they find another path, and so on. So in many ways, this is actually a universal phenomenon for kind of the runtime efficiency of iterative methods. And the other kind of supporting evidence is that if you look at the hard instances for a gradient descent, like the lower bounds on iteration count, they actually have the shape of graphs, and they do make it do this kind of very large number of propagations. Any questions about this example? So let me get to how people have been trying to fix this. And the general idea is that instead of finding an arbitrary path, what I really want to do is I want to find the shortest path at every step. So this is basically flow algorithms in the 1970s. And what they came up with is the idea that if I always find the shortest path, imagine I have I units of flow that I could still route. If I have I units of flow left to route, and they are all edge disjoint, there are m edges total. The shortest among these have length at most m over I. So in the most optimistic sense, in the sense that I always find you the shortest augmenting path I could take in the residual graph, the running time of the algorithm is sum over I from 1 to n of m over I, which is a harmonic series. And this harmonic series just sums up to log n. So in a very optimistic sense, you do get runtime that is close to m log n. So this means that subject to this magic oracle that's able to tell us what is the length of the shortest path from source to sink in this dynamically changing graph, max flow bipartite matching, pretty much all the optimization problems on graphs are essentially easy. And all we have to do is be able to dynamically compute this shortest path as the graph is being adjusted.
So the ith step, you mean all shortest path, all parallel?
For the ith unit of flow, I just route. I always route the ith unit of flow along the shortest path in the current residual graph.
Any one.
Any one. Because you have that the length is short, and that only creates a small number of updates to the residual graph. And that's how you can show that the total update size is reasonably small. Yes?
Maybe it's obvious, but why is the length short? Why I got confused on that. Why
the paths are edge disjoint. So there are m edges total. And there are I units of flow. So flows have path decomposition. Yeah, this is a kind of a fairly, it's a very interesting fact in that it kind of tells you like, hey, there does exist very simple representations that give you it gives you very efficient solutions. And the goal of the algorithm is really just trying to approximate this length in any reasonable way.
Like if I is equal to n, I know I should know this fact, but I can't see why. If I is equal to n, why is it m over, there's a path of length m over n?
So if I is equal to n, then there's total.
The first step, I guess.
Yeah, the first step, imagine you still have n units of flow left. So flows have path decompositions. Any flow that's from source to sink, there is a decomposition of it into edge disjoint path.
Okay.
The fact they're edge disjoint means just by pigeonhole, right?
Oh, I see. Okay, so you're saying I could do a flow decomposition. Yeah, sure.
Capacities are all one.
Yeah, I see. Okay.
Yeah, in the general capacity case, this is a little more tricky.
Could you repeat that? Press camera.
Oh, so yeah. Oh, I didn't know if you want to repeat too. So I guess you're saying like I can flow. Well, how many units? I do like what a flow from the one source from my source to the sink, and how many units of flow does this flow?
Well, suppose you have I units left to route. So instead of thinking how many units I have routed, think of how many units there remains to be.
There are I left to route.
Maybe he shouldn't repeat it I times. Maybe just go on.
Yeah.
But this is a fairly critical fact, and it is useful to pause a little bit too. Yeah,
so
because
we can think about it after too.
yeah, the general idea is just because my updates are edge disjoint, if there are I updates for me left to make, the cheapest one should have cost that is roughly m divided by I. And that harmonic sum is a very nice number. Except the problem is that dynamic pathfinding is one of the oldest unsolved problems in graph data structures. So this problem of checking, even a directed graph, even the following problem, which is I want to support a directed graph, and I want to find a path from source to sink, and then I want to flip the edges, and then I want to look for another path. This is a notoriously difficult problem in dynamic graph data structures. in that the way you can think about these issues is that, first of all, you have the highly connected graph situation, where if you update one edge, a lot of the it has a large neighborhood. So you need to update everything in its neighborhood. And this becomes expensive.
Excuse me, if you want edge disjoint paths, right? So you have one. So then those edges should, why don't you take them out of the graph instead of reversing their direction?
Because I could potentially pick the wrong edges to use.
But then you don't get an edge disjoint, another edge disjoint path.
So that's the notion of residual graph. The residual graph is if I use edge once forward, once backward, they just cancel. And it's as if I have not used the edge at all. So the flow algorithms that essentially require you to put once you use an edge, you have to put it in the reverse direction, just so that you can make sure you haven't used it in the wrong direction.
So you have directed graphs? Or?
It started off as undirected. I'm actually completely working with undirected graphs. But once you use that edge, it becomes this kind of directed notion.
Thank you.
And the problem is that I can also have very large diameter, in that sometimes you can think about, hey, I check an edge. I'm only looking for short path. I just check if it goes from source to sink. But then the problem is that imagine my source to sink distance is some reasonably small number, something like log n or log squared n or something like that. Then you need to do a reasonable number of propagations as well. So once you get graphs that are essentially the Cartesian product of these, you're onto a situation where every update essentially forces you to look at everything in the graph and then propagate information along. And in fact, this can actually be formalized, and there are actually conditional lower bounds that say that it's very difficult for us to do anything that's less than linear time in this kind of dynamic reachability problem. So the general issue with designing efficient flow algorithms is that assuming there's a perfect data structure, everything is happy, except this also happens to be one of the hardest data structure problems out there. So the solution that people have essentially came up with is to use the fact that we can actually find a representation of all the shortest path, also in linear time. That is, we can actually get rid of all shortest path in the time it takes to get rid of one path. And the way this gets used is in the Avantaja and the Hopcroft-Karp algorithm. What they do is they say we get rid of all augmenting paths of length I in linear time. Or in other words, they batch all the path length of a certain, for all values of m over I, because these are still integer values. They batch all those values. And this is how they arrive at a runtime that is roughly m to the 1.5. So the general idea that I want to kind of take away from this kind of algorithm is that the general kind of approach to getting better graph algorithms is that we try to boil it down to a data structure / update problem. But then we don't solve the problem. We try to batch these updates in the most aggressive way possible. We try to combine these updates. And then we try to avoid using these online data structures by going to the offline setting, which is a kind of a well-studied concept in data structures, where you're given what are your updates. You have some kind of prior information on what your updates will be, and you address it in that situation instead. And for this talk, I will discuss two problems where this phenomenon was very useful. One is a static problem, network flow. The other problem is the dynamic problem, dynamic matchings. And I'll talk about how the use of intermediate states, recursion and amortization, was critical to getting better algorithms for those problems. What am I doing for time? Is there a clock? OK. OK, great. Thanks. Thanks. So for network flow, as I hinted earlier, the idea is I want to update by a batch of paths whenever possible. And this is phrased in terms of, hey, I have a flow. I just add another whole flow to it, and I repeat. So this is the kind of idea that underlies the current fastest max flows. This includes the Goldberg-Rao algorithm. This includes interior point methods. This includes the almost linear or nearly linear time approximate max flow algorithms over the last decade. So the idea is that I want to basically find a max flow by averaging together a sequence of flows. And essentially it boils down to the following kind of approach, which is that imagine the following ideal algorithm, which is that I just have the residual graph. And every time I'm able to find a 2 approximation to the max flow in the residual graph. What does this do? The maximum amount I can route in the residual is basically the difference of my current flow value to and opt. So if I'm able to find a 2 approximation, I have just essentially halved my distance to opt. And I can just keep on doing this. And this will terminate in log n times to a very high accuracy answer. So the idea is that I can try to design this kind of iterative method where every time I just look for a global update, and then I update my solution value by it with a small step size. The problem with this is that the residual problem is about as complicated as the max flow problem itself. It's not very amenable to a lot of the tools in randomized / numerical graph algorithms we have developed over the past decade. So to make these things compatible with each other, what you can say instead is instead of saying I want to have a feasible flow in the residual graph, instead what I say is I want to find a change, this delta value. And I want to find a change such that the energy of the change is minimized for some potential function related to the flow values. And the wish list for this potential function is that first it should be convex, just to make it solvable. Secondly, I want it to be differentiable, so that I can start doing approximations, I can start throwing numerical methods at it. And the third one, which is the hardest one, is that I want it to be symmetric. In general, we are much better at preconditioning, sparsifying, approximating any kind of symmetric function. We're much better at doing that than for asymmetric functions. And the biggest issue with this max flow problem is that if you think about the function that says I need to stay within capacity, is that it's a completely one-sided function. As you get close to the capacity of an edge, you start getting to a situation where you can only go a little bit in one direction, but a lot in the other direction. And it's about as asymmetric as a function you can get. And that works terribly against our notions of approximations. So essentially, the crux of the problem becomes, well, once you start thinking about max flow this way, the crux of the problem becomes, how do I devise a residual problem where the functions that show up are also symmetric and are easy to approximate? And this is the point at which it's useful to turn to norm minimization, which is that almost all the flow problems we think about, they can actually be couched as norm minimization. In that the norm of a vector, right, is just taking every entry of the vector, take it to the pth power, and then take the whole thing and take it to the pth root. So the p equal to 1 becomes shortest path, p equal to 2 is Laplacian's, and max flow is actually the L infinity version of this problem. This has several advantages, one of which is you can draw them, and the second is that you can start drawing a kind of analog between the max flow problem and the 2-norm flow problem. And the 2-norm flow problem itself is particularly nice because it turns out there is a residual problem that you can solve very well on it, which is you just take the same problem and you just say minimize the L2 energy of the change vector. This is a symmetric problem, and it also has its undirected, and it also has a dual that is a matrix. So it's basically, among all the network optimization problems, this is one of the nicest ones out there. And essentially, we have fairly strong evidence that pretty much anyone's favorite algorithmic tools work for this problem, in that there has been basically essentially roughly every 2 or 3 years, somebody improves the exponent on the solver runtime. And the way this has been done was either graph partitioning, semi-definite programs, matrix concentration, Gaussian elimination, gradient descent, you name it. Your favorite tools work for this problem. But that raises the question of how much of this phenomenon is really restricted to 2 norms. A bit of a pie-in-the-sky hope that kind of a lot of people who worked on solvers were thinking for a while is, what happens if I'm able to just cross out the 2 and just putting an arbitrary norm for this problem? Somewhat surprisingly, this turned out to be doable. In that the residual problem for p norms, all you need to do is you need to put in, instead of just a 2-norm term, you put in both a p norm term and a 2-norm term. But a mix of 2-norm and p-norm is still a symmetric preconditionable function. It behaves nicely, it's symmetric, it's differentiable, it has all the nice properties.
So what is the interpretation of that in terms of graphs with a general p What does that mean?
So in graphs, what you do is you look at the amount of flow you put on every edge, and you take the p norm of the energy on that. So for max flow, what it is I want to minimize the maximum amount I'm routing on an edge. So I'm trying to route a flow while minimizing the congestion.
But why is the general p norm better than just the max flow or the shortest path?
So the reason is that it's an intermediate problem where these things are still differentiable. So it's an issue which this is what we can solve. Of course, we would like to solve the general p, and there is a still gap between arbitrary p and the L infinity version. But a lot of this preconditioning machinery starts to break down. So this is really an issue with the math at this point. So what we proved is actually that a lot of our tools for 2 norm can basically generalize to arbitrary p norms. In particular, what you can get is for any p norm minimization problem, you can actually get algorithms that just solve them by solving m to the 1/3 times p linear systems. For the flow problem on graphs, you can actually redo a lot of the preconditioning literature, and you can actually get algorithms that run in time that is almost linear, but multiplied by a factor of p. So to answer your question, the issue with getting p to infinity is that these algorithms still have a dependency on p that is linear. But the interesting thing is, aside from this p dependence, you're getting runtime that is basically looks the same as if it's 2 norm. So there's a couple of papers. But the general takeaway from this is that once you identify the right intermediate problem to look at, you can start adapting a lot of the technology, and a lot of the tools are able to work for this kind of problem. Questions before I go to the dynamic setting? Okay. So the story is that for a lot of the static problems, we do have a much better understanding of them, especially for undirected or problems with differentiable objectives. But the issue with a lot of these large graphs is they're not just static. The easiest way by which we get large graphs is we took the history of some server data log. We took the history of some database, and we just put everything together. And such graphs by nature are also dynamically changing. So the idea is that there's a notion of dynamic graph data structures, where you want to answer queries in time that is faster than looking at and reprocessing the entire graph altogether. And the general case with dynamic graph algorithms is that once again, we're very good at maintaining single or 1 or 2 paths. But as soon as the number of paths gets large for things like flows and cuts, right now, for a lot of these problems, the current best we can do is basically recompute from scratch. One particular interesting problem is dynamic matchings. This is a problem which is it's an easier case of max flow. And you can just view it as I have some vertices on the left, some vertices on the right, and I want to assign everybody on the left to everybody on the right while minimizing some cost. It's the assignment problem. And this is also something that recently has been used a lot in machine learning through what's called the optimal transport problem. And the issue with maintaining large matchings is that if I add an edge, it's possible that, hey, this edge was, this was still a maximum matching, but once I added this edge here, it's better for me to replace it with these 2 edges. And when a matched edge gets deleted, it's also useful for me to put it back in some other location in the graph. And the idea is I want to do this kind of change in time that is better than re-examining the entirety of the graph. There's been a lot of work on this. A lot of them actually got constant factor approximation, and they all had approximation ratio that is significantly away from 1. And the reason is that if I want better approximations, I need to look at longer and longer paths. It's possible that, for example, if I have a matching like this, and I added 1 edge on the top, the way that I can actually get to a bigger matching is I need to get rid of this, remove this, put this back, and remove this edge to get to this one on the right. So the issue is that implicitly underneath this dynamic matching problem, there is the need to find and remove longer and longer paths to get better approximation ratios. But as it turns out in the static case there, once again, you can batch these. This is actually a consequence of the Hopcroft-Karp algorithm, is that you can actually get to 1 plus epsilon approximation in time that is roughly m over epsilon. But that is linear in the problem size. Is there a way that we could leverage this kind of algorithm to design a data structure that does sublinear time per update? As it turns out, you can actually get some slight speedups when the answer is small. In that imagine my answer is 1. If my answer is 1, because we know that the size of the maximum matching is the minimum vertex cover. When my max matching has size 1, all my edges are incident to a single vertex, and I just need to keep a small number of neighbors of that vertex. You can actually take this idea a little further. You can actually show that if your opt size is opt, you can actually reduce your graph size to one that's roughly opt squared. This is through kernelization. But this does not address the case where opt is large. So once again, there's the issue is that where opt is large, I still need to look at the entirety of my graph in order to get a reasonably good approximation to the size of the maximum matching. And the way that this got addressed was actually very interesting. In that all we did is we say that, hey, if the size of my answer is opt, and I have a 1 plus epsilon approximation to it, as I make updates, I can only change my answer by 1 at every step. So this answer will still remain an epsilon approximation for up to epsilon times opt steps. And then if you do amortization, what you get is that you get a cost that is roughly m divided by opt plus opt, which by just optimizing for parameters, you get that this actually comes out to roughly square root of m. Even more surprisingly, you can actually make this work for weighted graphs. And you can also make this worst case, and you can do everything with it. At the time we did this, we thought this was a very limited phenomenon that's only useful for maximum matchings because the answer is stable as you make single updates. As it turns out, this idea gets used a lot in a lot of dynamic graph algorithms now. It gets used in graph sketching, gets used in network centrality, it gets used in connectivity and dynamic MSTs, all which are fairly non-robust objectives. And the way this ends up being done is that every one of them has some kind of approximation underneath the data structure. And they do these kind of gradual updates with some lazy tracking so that they can do kind of global reprocessing after a while in a way that still lets them keep the cost per update down. And recently, we even have experimented on real-world graphs using some of these network centrality type ideas. So once again, this is an example where it's possible to remove all short path by doing some very global thing. But then here it's happening in a dynamic setting. And the key is to amortize the cost over a large number of steps. Any questions? So before I move to the summary, I want to mention two. Chris?
Sorry. So wait, what exactly is this the amortized cost of? This is for if I'm maintaining. Can you say exactly what's the square root of m go for?
The square root of m is I can maintain 1 plus epsilon approximation in time that is root m divided by epsilon per update.
So for like dynamic maximum matching?
Yeah, dynamic maximum match and weighted matching, all these things.
But sorry, so what's the offline then?
The offline thing is that you're just recomputing a matching.
So you're saying though it leads to a faster algorithm now in the offline case?
It actually leads to a better data structure for online maintaining matching.
I see.
So just calling this offline scheme actually gives you a better online data structure for maintaining matchings. So before I get to the end, I want to talk about two slight asides, which is really kind of illustrates what kind of things out there can be done with graph theoretic tools. The first is this optimal transport problem in practice. So this problem that has been a lot of attention given to machine learning because it can be used to do as an adversary in generative adversarial networks, and also because it was used for text embeddings, word embeddings, and so on. There actually has been quite a bit of work on trying to couch this problem as a matrix problem, and doing what's called matrix rescaling, Sinkhorn, Greenhorn methods to get to good matching solutions. So this is a result. It started with a work in NeurIPS 13. There was a work in NeurIPS 17 that sped it up. And there was also recent work that did slightly more combinatorial things to it. But what we found out is that once we took the data, we extracted data, and the problem essentially was a min cost perfect matching problem on a very dense graph with about 1,000 vertices. And what we found is that once we extracted these data, we took them to C++. And we just ran the C++ operations research packages, which are really optimized for dealing with sparse graphs. We get significantly better runtimes. So at least for some of these instances, especially dense graph problems, you can actually just almost running off-the-shelf tools can give you significantly better performance than these existing numerical methods. But this is a very unexplored phenomenon in practice, I claim, because we haven't really done a lot of these kind of practically driven efficient graph algorithms for machine learning related instances. And we haven't even started adapting them to the kind of the approximations or kind of the structure of these problems. On the more theoretical side, I want to bring back to the slide earlier by Anna on Floyd-Warshall algorithm, which we probably have all done in undergrad algorithms. Right? So the idea is that you're trying to compute the distance in a dense graph with a matrix in a distance matrix. So the idea is you just loop through all indices ijk, and you update the distance values. Right? So you just update the distance if possible. I guess it's double blurred now. The initial version was slightly blurred, but I guess this is useful. Everyone has seen this algorithm, right? How many can tell off the top of their head what are the order of the 3 loops? Which one do you loop through first? Which one do you loop through second? Which do you loop through third? I always write it as ijk. Turns out that that's wrong. As it turns out, recently there was a paper, almost posted on April Fool's Day, that says that no matter how you do how you do the order of these 3 loops, you just run your algorithm 3 times, you will get the correct answer. This led to a lot of memes, and as you might expect, I mean, part of the reason I took the photo was that I'm now sitting on a Slack with a bunch of these people who have taken this undergrad algorithms class at Waterloo. And we have this Slack, and some of the people on the Slack say that they get unreasonably excited when I see a Floyd-Warshall problem for this kind of reason. And the way that this gets proven is actually by going into it and decomposing the distance, look at the runs in the distance, and actually do a very fine kind of combinatorial analysis of what the distance structure of it.
Is this one actually wrong? To do it once?
This one's actually correct if you do it once. I think you have k outside and then ij. But the point is, if no matter what order you do it, there's this kind of very weird high-level phenomenon is that you take graph algorithms, you start iterating on them, you can get very weird behavior. And this kind of iterative kind of ability for graph algorithms to fix themselves is a phenomenon I claim is very not understood. And it could lead to a lot of new ways of getting better provable runtimes. So in general, I claim that efficient graph algorithms, to get even more efficient graph algorithms, what we really are missing is we're missing a lot of ideas from data structures, especially combinatorial algorithms. In the sense that a lot of what we're currently doing can be thought of as we're trying to basically get faster dynamic pathfinding. And what we really should be doing is just avoid them whenever possible. For example, with flows, we went to p-norms, we went to residual networks, and we started doing preconditioning. With matchings, we went to vertex cover, we started doing amortization, and we started doing kernels. This is an idea that is still very active in recent works. Recently, there has been some progress on getting this kind of things to work for C-edge connectivity, which is that instead of having just maintaining 1 connectivity or 2 connectivity, now there are results that they're able to maintain arbitrary connectivity values. And also on the flip side, it turns out that some of these ideas, the connection to graphs is even useful in the data structure setting, is that you can actually show some separation between online and offline data structures. Namely, basically you can actually show that certain kinds of heaps cannot have dynamic optimality by looking at the access sequence from shortest path algorithms. So in general, I think there's a lot of very rich connections between graph and data structures, and I hope that there will be more work in this space in the near future. Thank you.
Is there any basic reason why the 1 over epsilon, poly 1 over epsilon dependencies for the flow problem cannot become log?
Oh, for the flow problem, the poly 1 over epsilon. So this is a situation where for combinatorial algorithms, I mean, in general, you take any flow algorithm, you just say anytime I push flow, I just push it to the limit, and I just kind of keep on doing approximation in the residual graph. This is a situation that is very hard to produce actually in practice. So I think a lot of what's missing there is there's a lot of basic theoretical kind of tools and analysis tools we're missing, because in general, we're not very good at analyzing how functions without gradients can be kind of approximate each other.
The true bound might actually be much better than poly 1 over, might even be low.
So max flow as a practical problem is, I mean, the way I tell people about max flow as a practical problem is I say that we know how to solve linear systems very well in theory. We will be lucky if we ever get linear system solver for graph Laplacian that runs as fast as max flow packages in practice. So max flow packages in practice is about 100 clock cycles per edge. And there are very few examples where they even take that long per edge. So this is as kind of a practical problem. The hard problem for max flow is really when you have costs in there as well. You start doing things like min cost flow, or you do like general optimization objectives. Because they're so pathfinding based and kind of optimized for path, that they're actually not very good at like adapting their algorithms to deal with this kind of, the more numerical kind of structures in there. So I think a lot of it is just we don't have very good notions of preconditioning for things without gradients.